So we will be talking about something actually pretty interesting today. Two forms of sort of like alternate machine learning paradigms. One is quantum machine learning, and another is optical neural networks. You might have heard some of these in the past. They are fairly, I think, popular in media and whatnot nowadays, or you might not have. Both are possibilities. Okay. All right, so the sort of lens we're going to be looking at quantum machine learning through, at least, will be support vector machines. So I'm going to basically sort of go through a classical theory sort of explanation of support vector machines, and then we'll talk about the quantum version and why it may be useful. So the sort of basic SVM, support vector machine, sort of model is just a supervised learning model that seeks to divide classes of data into separate classes. So for instance, if you wanted to build a support vector machine that classifies cats and dogs, then you would have data points of cats and dogs. Maybe it would be the dog has a face shape like this and the cat has another one. And you find these distinct features that you can then divide with a hyperplane. And so that sort of just looks like this. You have these two classes. So one is maybe green triangles and one is orange rectangles, and they're clustered around various regions. And you try to draw a plane through those two regions to kind of separate them. So we'll say basically, oh, if you fall on this side of the hyperplane, then we'll just call you green triangle. And if you fall on that side of the hyperplane, we'll call you orange rectangle. And as you scale up into different dimensions, then you can have hyperplanes of different geometries. So in this instance, we're looking at a 2D plane. So we have a line basically as our class divider. But when we scale up to something like a 3D plane, we can have actual planes as our dividers. And though it gets hard to visualize as dimensions get higher, there are sort of just different geometries for different planes. Yeah, and if you have any questions on the way here, feel free to just stop me whenever. And so as we get into more complex problems, the sort of classification of our hyperplanes, of drawing hyperplanes and sort of perfectly splitting two classes becomes difficult. You can see for data like this, it's kind of difficult to just draw like a line that will just perfectly segment these two paths, regardless how you cut it. Like if you cut it this way, perhaps you're going to end up with data that will mix into different classes. So you can't really evenly draw some sort of linear line through this thing and exactly separate our classes with high accuracy. Now, in the case of a neural network, that would be, or sorry, not neural network. In the case of doing classification with a support vector machine, this would be pretty bad and pretty difficult to deal with, as we would just have low accuracy if we were to sit in 2D space. Well, one trick we can do with support vector machines is we can actually go into higher dimensions. So we can take this 2D set of data and we can transform it into a 3D set. And you see now that it's in 3D space, we can easily draw a hyperplane instead of a line that cuts the data right here. And then we can just say, oh, if you're above the hyperplane, you are blue, and if you're below the hyperplane, you're red. So by transforming our data, we can actually generate an SVM model that's fairly accurate. So that's sort of the key thing here about SVMs, is that even though you oftentimes have data that is difficult to separate, by changing dimensions, by going from 2D space, where this data would otherwise, would be otherwise inseparable, you can change it into 3D space, for instance, and get this nice and clean data that you can then draw a plane through. And we can do this with higher dimensions as well. We can take data that perhaps is difficult to separate in 3D and then change it to like 4D or 5D, etc., and find better ways of classifying it. Now, one thing to note there is, that this mapping, this function mapping of saying, oh, I have a data point in 2D and I want to bring it up to 3D and 4D and all the way to like N. This can be very computationally expensive because you basically have to have a function that sends every data point to a different sort of dimensionality. And that, especially for higher dimensions, that can be very, very costly. So one way that folks have developed to kind of get around this problem is this thing called kernels. And kernels are basically the crux of SVMs. They kind of dictate how this function mapping, this sort of mapping to higher dimensional space occurs. So kernels are a little odd. I guess we won't really get into the exact mathematical theory of them because they kind of involve a good amount of linear algebra to start with, but we can kind of generally talk about them. So what exactly is a kernel and why do we want to use it? So because of how SVMs are constructed, we may want to send data to different dimensions. And the thing here for SVMs is we're doing a classification task. So we only really need to know how the data sort of acts relative to one another. How is a cat different than a dog? We don't need to map all of the cats to a different plane and all the dogs to a different plane. We can simply analyze sort of the relation between cats and dogs. So instead of transforming each individual point, taking each x to each fx and each y to each fy, if we're sort of performing classification tasks on x's and y's, we can actually just examine the dot product of these sort of different things when they're raised to a function. So that's what we're going to call our kernel. Our kernel is going to involve just an inner product or dot product of these sort of transformed pieces of data. And thus we see that we don't actually have to like store all this data and transform all this data to a higher dimension. We can just analyze how the dot products between each of them behave when we go to higher dimensionalities. And this is quite computationally sort of less expensive. And we can sort of see that in a couple of examples here. So for instance, if we wanted to take our data, like maybe 2D data, x's and y's, and send it to a polynomial dimension, so squares here, for our actual function, for mapping a function and sending all of them directly there and getting an fx for each x, we would have to put each x and y into this function. Whereas if we're only to examine polynomial kernels, so how they are related to one another by taking inner products between x's and y's, our kernel function is simply this expression, which is much more simple than doing something like this. And this point is sort of exacerbated as you go into more complex kernel functions. So that, yeah, go ahead.
Is the idea of SVMs like taking some sort of data and blowing it up into different so that we can draw hyperplanes?
Yeah, so the sort of, yeah, it's basically we have maybe data that's hard to classify in the original dimension it's given in. So as you saw from this example here, like this data was hard to classify in 2D. And so we could use a transform to send it into 3D space, and then we could then draw a hyperplane through it in a much sort of easier manner. And that's sort of one of the big ideas behind SVMs and how you get to these nice inaccurate models. So we'll talk about this in a second. That's sort of we're going over a very general outlook, and then we'll talk about the actual support vectors behind the support vector machines in a second. But yeah, so we have these kernels, and then we can even look at something like this radial basis function, which is another kind of. So if we were to perform this radial basis function, this mapping operation, the actual radial basis function would be some infinite dimensional mapping that is actually incomputable. But if we were to apply it as a kernel, then it just becomes this e to the negative gamma, and then in the product of x minus y squared. This gamma here is just a sort of parameter that you can use to determine the spread of the kernel function. But this sort of illustration is pretty powerful in that if we were to take our sort of original function mapping and say we want to send x and y to some dimension based off the radial basis function, we can't actually compute the function, but we can compute the kernel. And so that's a sort of very big advantage of kernels. We've sort of reduced this infinitely costly function into something that we can pretty easily compute and do very quickly. And so yeah, just to summarize, we only care about sort of the pairwise similarity comparisons of our data. We don't really have to apply an entire transform to it. So instead of using functions, we can just use these kernels. So we've talked about some basics of SVMs, and we'll look at some like a sort of more descript version of it. we'll look at it in terms of vector interpretations now. This is where the actual support vector part of the support vector machine is going to come in. So first off, we talked about sort of just drawing a simple hyperplane or drawing a simple line through 2D data. We're going to kind of look at a more in-depth kind of concept here. So another thing we care about when we draw these lines and these hyperplanes for our SVMs is we care about how big the margin is. So we see here in this example, there's a pretty small margin in our SVM. So there's only this much distance between the closest point to the sort of decision boundary, the dividing line, and the sort of other side of it. And the closer your points are to the decision boundary, the more likely that you're going to have some confusion. So if you have a small margin and you read a new data and your decision boundary doesn't really distinctively divide your points super well, there's a small margin, it's more likely to sort of maybe accidentally fall under this side. So when we draw our hyperplanes and support vector machines, we want to maximize the margin basically. So like for instance, in this example, we have a large margin, so all the data is quite far away from the decision boundary, we divide it very well. And if we were to look at an example, if we took like a new data point, right, and it fell maybe here, it's possible that in this SVM, that data point would accidentally get classified as a blue rectangle. But if we put a data point in the same position, like right here, on that SVM with that large margin, then it's going to end up as the correct piece of data. It's going to end up being classified as a green circle or diamond or whatever that is. Any questions about this concept of margins? Yeah, so at the end of the day, we just want to maximize the margins. And this is when we can begin examining our data points and viewing them as vectors instead of just data points. So each of these, let me actually go back a bit. We can look at the sort of points that are closest to the decision boundary as vectors. So in this case, we want to maximize the distance of these vectors from the decision boundary. And we also want to make it so that a lot of them are actually orthogonal to the decision boundary, or they're sort of 90 degrees away. And just to sort of quickly define a vector consists of a magnitude and a direction. So here we care about how far away it is from the decision boundary. And if we were to just draw a line from the data point to the decision boundary, how would it be facing? What direction would it be pointing in? Now, for these vectors, to maximize the margin, we want to maximize the magnitude, and we also want to make the angle of these lines to be sort of orthogonal, because that will basically dictate a decision boundary that is far away from the most data points. And so that's the support vector part of the support vector machine. We have basically this expression of the hyperplane as individual sort of support vectors, how far away your closest data points are in magnitude and in angle. And we actually use that information, those angles and those magnitudes, to decide where to put our hyperplane. So we're basically trying to collect as many data points that are far away and are orthogonal to our decision boundary. And that's one way of deciding where to put your hyperplane. Yeah.
I think I'm sort of confused about like how we're counting orthogonality from the individual points that are closest to the decision boundary. So do you mind just like showing how you actually see what it is orthogonal?
Yeah, so sorry, I should probably clarify that a bit. So I can actually draw a picture of some new decision boundaries, and I'm doing that with a mouse, so we'll see how that goes. Yeah, so let's say we have a set of data points. Let's say we have some blue ones here. Let me make this really thick so it's really easy. Okay, so we have some blue data points here, and we have some, let's do red. We have some red data points over here. So on one hand, we could draw a decision boundary, maybe like so. And we could have some sort of margin. And so if we looked at how these vectors were in relation to the decision boundary, we can draw them like that. And these ones we could draw like that. The closest ones. And I guess this concept of orthogonality is less so, I sort of misspoke there. It's more so about, like if we examine orthogonality, if we draw vectors so that they're orthogonal to the decision boundary, then we can know that that's sort of their maximal distance for if we look over all of them. So in this case, we're drawing all our vectors orthogonal to the decision boundary, and we're sort of looking over, these are all the distances we have on the left, and these are all the distances we have on the right. And if we let's say we sum all those up, we say that's sort of one method of drawing a decision boundary, and we can sort of quantify how good that is. And then let's say we drew another one that's like this, and then we, okay, I'll probably draw a better line. Let's say we draw another one that's sort of like this, and we drew all our sort of distances to the decision boundary, and we drew them as orthogonal vectors. You can sort of see in this green case, as compared to the black case, our vectors have a much higher magnitude when they're drawn to the green boundary. So we would say that the green boundary is a better decision boundary or a better hyperplane. And the actual sort of SVM training phase would involve looking over these different hyperplane or / decision boundary combinations and seeing which one maximizes this orthogonal magnitude of these various support vectors, aka our data points that are closest to the boundary. Yeah. Yeah, so there's a mathematical way, but it's kind of freaky looking, so we won't sort of talk about it too much. But yeah, hopefully that clears things up a bit. But yeah, the support vectors are sort of the key to getting a robust and accurate SVM, and we want to use those support vectors to maximize the margin. So let's look at this now, this kernel now in terms of our vector operations. So I'm first going to define a vector space. So a vector space is a set of vectors and a set of scalars that are closed under vector addition and scalar multiplication. What exactly does this mean? Well, that's basically saying that a vector space consists of a couple of vectors, and then you can add those together, subtract those, whatever, and you have a set of scalars that you can multiply these vectors by and scale their magnitudes by these scalar values. And so in a pretty common example of a vector space that you see pretty often is this these two 3x1 column matrices. So there'll be just U1, U2, U3, and then V1, V2, V3. And we see that we can designate this vector space, which is W equals AU plus BV, and thus reach this new sort of collection of vectors where we're performing scalar operations, multiplying by A on U1, U2, U3, and then performing scalar operations, multiplying by B on V1, V2, and V3, and then we're summing those two vectors together, the U and the V vector. And so we can see that W is a vector space that is comprised of U and V. And so actually, if you look at this vector space, you see that we can pretty much reach any collection of 3x1 vectors with this by changing around the scalars and then by changing around the U1, U2, U3, and V1, V2, V3 values. And so this is a pretty common vector space. This is the R3 vector space. And you can kind of just sort of imagine the different scalars and vectors you can put into that to kind of go to a lot of different vectors. And so in this context, then, we'll treat the kernel as something that takes some input vector in its original space and then gives us back the inner product of the vectors in a different vector space. So we're basically taking a lower dimensional vector space and then using the kernel, putting those lower dimensional vectors into the kernel and producing this higher dimensional vector space. And so it's pretty similar to how we thought about it earlier, just kind of taking inner products and putting them into higher dimensions. But this time we're just going to call these things vector spaces. And we're still doing the same things. We're going to take the kernel. We can use this kernel to transform our set of support vectors. And in that new vector space, we can then perhaps draw a better decision boundary that'll maximize the margin more and enable us to sort of classify the data in a better way. Yeah, the idea of a kernel is just to enable us to conveniently come to a higher dimensional vector space without performing a lot of expensive computations. And so we've been talking a lot about classical neural sort of machine learning. And the question here is, where does the quantum mechanics factor into all of it? So a big thing here is complexity, right? We've talked about sometimes that there are functions that require infinitely too much computation to sort of actually transform data points one by one into a higher dimensional space. We have this kernel trick that enabled us to sort of do that in a more simplified way. But sometimes even kernels can sort of require lots of computation if the dimensional space is very high, or if the vector space that we're trying to get into is quite inconvenient for kernels, classical kernels, to deal with. So we'll briefly talk about quantum computers. So what is a quantum computer? Well, in a very simple and high-level definition, we can kind of think of them as computers that run on these things called qubits instead of classical bits. So what's the difference here? Classical bits are either a 1 or a 0, so they're called binary. They can only be in a 1 state or a 0 state. In transistors, if you have an electrical signal that is over a certain threshold, something's going to be in the 1. If it's under, it's going to be in the 0. Now, a qubit is a little bit more complicated because the quantum principle of superposition enables us to have bits that are a probabilistic mixture of both 1 and 0. I've taken any linear algebra courses in the past. You can think of it as a linear combination of 1 and 0, but for the time being, if you don't know what that really means, probabilistic mixture is a decent hand-wavy explanation of that. So let's just look at some basic raw numbers and see how classical bits represent them and how you can represent them as quantum bits or qubits. So classically, if you have a 1 or a 0, then it's a 0 or it's a 1. When it comes to qubits, though, we have these states. We'll call this state psi, and it'll be equal to this alpha times the 0 state plus a beta times a 1 state. And what does that exactly mean? Well, that means that we have this state psi, and it has some probability alpha of being in the 0 state, or this isn't exactly probability, but we'll call it a probability amplitude. It has some probability amplitude of being in the 0 state, and some probability amplitude beta of being in the 1 state. So prior to measuring this qubit, it can actually be either in the 0 or the 1 state. This is sort of the famous Schrodinger cat example that folks like to talk about. The cat can be dead or alive prior to measuring it and knowing that it's actually dead or alive. I think it's good to clarify here that we don't actually have both a 0 and a 1 state, but we can probabilistically reach either. At the end of the day, once you measure the state psi, we are going to end up with a 0 or a 1, but we can reach both of them with just a single qubit. So let's look at more bits and see why this might be useful for us. So we see that for 0 and for 1, we've represented these two classical bits in a single quantum state, a single qubit. Now let's get into 2 bits. So let's say we have 2 classical bits. We have a 0 and a 0, a 0 and a 1, a 1 and a 0, and a 1 and a 1. So these are 4 different configurations. If we have 2 bits, these are all the configurations that the system can be in, and we will need to actually just represent all of them straight up. We can't sort of say, oh, I'm going to use less combinations to show all of these classical bits. We're going to have to represent them. So in the terms of qubits, we can say that we can represent all 4 of these classical states with just the state psi1 and the state psi2. And why might that be? Well, it's very similar. We have this alpha 0 and this beta, we have this alpha and this beta. That gives us some probability of being either in the 0 or the 1 state in psi1. And we can have the same thing for psi2. So we see that we can actually reach all 4 of these sort of classical states with these 2 qubits by just saying that probabilistically we can be either in 0 or 1 in each of these states. And thus we can measure possibly either of these 4 sort of classical states. Any questions on this idea here? Okay, perfect. So the sort of really nice thing here then is we see we've actually managed to represent all 4 of these classical bits with 2 qubits. Up there we represented 2 classical bits with 1 qubit. And so the nice thing here is that we can actually, in general, we can represent 2 to the n classical bits with only n qubits. And this is really quite useful for a variety of tasks. The sort of low-hanging fruit here is if we want to run a simulation, perhaps, of quantum chemistry where there's a lot of quantum particles, each that are described by these superpositions. We can't really do that with classical bits because we can't represent all of these possible superposition states of each of the classical, of these sort of quantum particles moving around in our simulation because we simply don't have enough bits. And I have a below example of showing why that might be. Yeah, so these actually blow up really quickly. So let's say I had a system of n equals 500. Let's say I want to do a quantum chemistry simulation with n equals 500 particles, each with a possible superposition. We would need 2 to the 500 classical bits to do that, which is more than the estimated number of atoms in the universe. So that's not really possible for us to do. Even a seemingly small amount of quantum particles in a simulation of just 500, we can't do on a classical computer at all. That sort of exceeds all of our possible computation. But if we had a quantum computer and that had 500 quantum bits, then we could easily perform that quantum chemistry simulation and describe all the possible states our particles could be in. Now, this has some other implications for things like cryptography, communication, etc., but we don't really go into those. I just kind of want to show the fact that we can represent a lot of these classical states very efficiently with quantum states. And here's this warning again. We don't actually have all of these 4 classical bits. We simply have the capability of reaching them. There's sort of no violation of conservation of energy or matter or all that. We do have 2 qubits, but we can only end up with either one of these 4 sort of classical permutations. We can't have all of them. When we measure, we're only going to end up with 2 bits, 2 classical bits. Does that all make sense so far? So if we have this quantum computer paradigm that enables us to sort of encode a lot of information with not that many bits, does anybody have any guesses as to why that might be useful for SVMs, in which we care a lot about how computationally efficiently can we reach these different dimensional spaces with these kernels and functions and all that? Anybody have any guesses? Okay, so we have this method of representing a lot of information with not that much stuff, I guess. So in this case, in the case of kernels and SVMs, we can actually go to higher dimensional spaces with less sort of operations if we use qubits in certain circumstances instead of classical bits. And we can actually physically show that that is a thing. But yeah, so in SVMs, we talked a lot about vector spaces, and actually, much of the quantum paradigm is described in terms of vector spaces, and each of these qubits represent sort of little vector spaces with their own sort of basis vectors and all that. So by using qubits, we can actually get to very high dimensional vector spaces without all that many qubits, and this becomes useful for SVMs in that we can perform these quantum operations and that enable us to project into higher dimensions with quantum kernels instead of classical kernels without using as much bits of computation. So we can actually look at some examples of that over here. So this demonstration is sort of from a paper that was published a while ago, and this paper, you might kind of think of it as cheating in that researchers basically generated a set of data that is hard for classical computers to do and easy for quantum computers to do. This is a set of data that's what you want to do a sort of classification task on and make a sort of SVM to determine different classes. In this case, this data, you can create a kernel, a quantum kernel out of it without much computation, but actually when it comes to just classical operations, you're going to struggle quite a bit to get a good kernel that will enable you to have data that is accurately separable. So if we just look real quick at what they did here, they have this set of fake data they generated that was purposely made to be hard for a classical computer and easy for a quantum computer. And then they basically do all of the SVM operations. So here they're making this feature map, which kind of describes how they're going to project these data points over here into a new feature space, a new dimension. Then they make some quantum SVM, do a bunch of operations on it, and basically seek to separate the data, draw hyperplanes, and find out the best way to classify. And in this case, for the quantum SVM, they actually have a success ratio of 1.0. And you may be thinking, oh, that's sort of a BS result because their data was built to be able to be well classified by quantum SVM, but that's just how things are sometimes, unfortunately, when it comes to research like this, where people want to show really good results. So with our quantum SVM, we have a success rate of 100%. You can see here the ground truth, where we have these A's and B's, these two different classes. The prediction separates them perfectly. And then this is their sort of kernel they built. So they take the same set of data and they use a regular classical SVM to do a set of classification on it. So they take the SVM function and they just take the training and the testing stuff and they plug it in, and their testing success ratio is a lot worse and their success rate isn't very good. And so you can see that the quantum SVM actually outperformed the classical SVM, and that it probably found a better kernel and it found a better set of features that enabled it to kind of split the data up. And the quantum kernel that was used here outperformed the classical kernel. And you can see here actually from these two different kernels, just by looking, that the kernel here, just from how complex this image looks, appears to be in a much higher dimensional vector space, whereas the kernel down here is much more simplistic in the lower dimension. And so this is sort of just an illustration of the fact that these quantum kernels can be advantageous over classical kernels, and that they can take you to these higher dimensional vector spaces much quicker and much more in a sort of cheaper fashion, if we're not counting all of the defects that come with quantum computers. Now, it should be noted that this is just a research test case in which a group of researchers sought to prove that quantum SVMs are actually useful and they're not just a bunch of junk being peddled by people in hopes of putting the word quantum in front of more things. In a lot of actual scenarios, using a quantum SVM isn't actually worthwhile. Classical SVMs already do very well with a very nice set of sort of pre-existing kernels and pieces of data. And they also do this other algorithm on a real-world data set. And they do the same thing, quantum SVM and classical SVM. And you see here the quantum SVM with its quantum kernel does pretty well. And the classical kernel does a little bit worse, but not much worse. So I guess at the end of the day, the sort of statement here is all the sort of baggage that comes with the quantum computer worth your 0.05 additional success ratio? Maybe not, but it does do a little bit better here. But yeah, this is basically the sort of illustration of a quantum machine learning algorithm. We've only looked at SVMs as sort of a demonstration example because it's nice and clean to talk about the fact that we can reach these higher dimensional spaces perhaps more quickly with qubits instead of classical bits. But there's actually quite a bit of work being done on sort of other quantum machine algorithms that also use this sort of superposition and the fact that we can encode more classical bits with fewer quantum bits. You can look at stuff like quantum principal component analysis, and there's also, I think, quantum neural networks that people are trying to make. But yeah, this is our sort of quantum example. Any questions on this? Okay, so we're going to shift gears now, and we're going to look at optical neural networks. So there isn't really anything, I guess, non-classical about optical neural networks, but I guess they differ from artificial neural networks, or the ones that we're sort of used to, in that they use photons instead of electrons as their sort of principal particle. Now, before we begin talking about how they're exactly implemented or what these sort of realizations and uses are, we're going to ask this motivating question. Optical neural networks are mainly sort of well-liked or sort of a hot topic at the moment because deep learning is actually quite expensive, despite the fact that we can do it fairly easily on our computers with all these wrappers and whatnot. So we're just going to look at this example real quick and see why that might be. So I'm just going to run through a basic sort of example of the MNIST dataset, which is a set classification task that seeks to classify a set of handwritten digits. So you'll see here, there's just this batch of different numbers. There's these hand-drawn numbers from 1 to 7, 1 to 9, and people are basically trying to label these when they're read in by computer as, hey, I'm given this picture of a number, what number actually is it? Here we have this image of a 7, and it's read in as a 7. So what exactly is this illustrating? Well, this is an image processing task. And to make these images into something that's computer readable, we have to do a couple of sort of operations to them. We have to make them into matrices that are these mathematical objects that our computer can then sort of mess around with and manipulate and give us some sort of output. So here, when we use all these PyTorch data loaders and these tensors and all these normalization functions, we're actually taking the pixel values of our MNIST training set and turning these images of hand-drawn digits into matrices. And while we do that, we can actually see what the shape of this matrix is. So this little 7, very pixelated and low-quality image, this 7 is 28 by 28 matrix. So that's already pretty big, right? If we think about matrices, like a 28 by 28 matrix, if you had to like go, if you were in a class and somebody asked you to multiply two 28 by 28 matrices together, you probably wouldn't be very happy because that's just a stupid question. But for a data set of just 1,000 images, we already see that we have this tensor of 1,000 by 28 by 28. So just think of like a 28 by 28 matrix and then projected like over 1,000 times. So that's a huge matrix already. And this is a fairly simple data set with not that many pieces of training data. When we had like a really, really big image classification task, for example, that was seeking to do something more complex, like classifying faces, our images probably would be bigger than 28 by 28, and we would probably have more than like 1,000 samples. So we would have massive tensors and really, really big matrices that we'd have to multiply together. And so like if we had an image like this, a much more complex and high definition image, it would require a way, way bigger sort of matrix to represent. And that leads to problems. So if we want to do a lot of computations and get an answer out, we're going to need some more specific architectures that will enable us to do this repetitive, albeit sort of simple task very quickly. And that's where sort of GPUs came along. So deep learning basically involves a lot of multiplication, matrix multiplications and operations on these really big matrices. And so at some point we sort of figure out that CPUs perhaps aren't really good for this, and we want to use this thing called a GPU. So what is a GPU? Well, I'll show you these two pictures, one of a GPU right here and one of a CPU right here. And sort of the immediately noticeable thing here is that all of these green things in the GPU, they represent sort of different sort of arrays that hold a lot of cores. So in this GPU, this RTX 3080, there are actually, let's see, 8,704 cores. And all of these cores can be doing these matrix operations. And the CPU down here, this Zen core here, as you can see, does not have all that core cores. Usually CPUs, you'll see you can buy them in like 4-core CPUs or 8-core CPUs. And that's sort of a paltry number when you compare them to this sort of 8,704 core GPU. And so you might be asking the question of, why don't we just make a CPU with lots and lots of cores? Well, the difference here with these GPU cores that are sort of much different actually than the CPU is that the GPU cores here are actually quite stupid. So they're really good at doing very simple tasks, while the CPU shown down here is good at doing a wide array of tasks that require much more complexity and sort of much more thinking, I guess. GPUs are really good at doing a lot of these matrix operations repetitively over and over and over again. They just have to do their one stupid task a lot, while the CPUs can do things like executing code or word processing and all that, although that's sort of not mutually exclusive. And that's why GPUs, in this instance, if you know sort of about computer games and rendering graphics and all that, are also very well used in sort of like video editing, rendering graphics for games, in that we have to render and rasterize a lot of these pixels and images in games and in videos, and thus this repeated sort of execution on a lot of cores can enable us to do that very quickly. So GPUs were actually a really, really big part in allowing deep learning to improve and not be so bottlenecked. Because if we were to do these deep learning algorithms that involved tons and tons of matrix operations on CPUs, they would basically take forever. So GPUs were a big part in why deep learning became much more popularized, I think in the late 2000s, I want to say, but don't quote me on that. Any questions on this so far? And it should be additionally mentioned that GPUs are doing all these computations in parallel. So they don't do like, all the cores can work on different matrix operations at once. And there's lots of clever algorithms as to how they're designed to be able to do a lot of these operations in parallel. Yeah, any questions on these architectures? The sort of crux here is just think GPU, very dumb, but can do a lot of work, while CPUs can't do as much work, but they can do sort of much smarter tasks. And so what might be a drawback of sticking 8,704 cores on a single card and trying to run them? I'll show some images and we can try and come to a conclusion on that. So here's a image of a video card, which holds a GPU and a couple of other components. Note which component is the biggest thing on this whole card. We can scroll down here and see that somebody's actually advertising a heater that mines Bitcoin. Bitcoin being something that people with GPUs like to mine. We actually here have another Bitcoin energy use estimates. They kind of are going into the like 70 terawatt hour per year. Terawatt hour per year, yeah. So anybody have any guesses as to what drawbacks GPUs might have? Yeah, Hannah. Yeah, they're really hot and they consume a lot of energy. We have a lot of cores doing a lot of parallel processes, and so things are going to get hot, things are going to suck up a lot of energy. So yeah, that's going to be a problem that lots of people are going to want to address. And that's where optical neural networks come in. If we just take the electrons, which cause the heating and cause the energy consumption, and replace them with photons, hypothetically, all of our problems should disappear, right? This is the principal problem that people are trying to solve with optical neural networks. They're trying to basically reduce the power consumption and the heating of GPUs. So we're going to basically talk over some basic architectures for optical neural networks, how they work, and how the different components kind of map onto the same classical neural networks, artificial neural networks as they're called, that we're used to. So machine learning, deep learning in this case, works basically by a series of matrix multiplications, some activation functions that transform these matrices into outputs that we like. And these operations are done repeatedly throughout training. They're iterated over a bunch, and they take a lot of energy and a lot of heat. So we're going to need to replicate this operation, this matrix multiplication, somehow with photons, with light, and with optical techniques. So we're going to look at how to do that. So before we get started, a very high-level overview of optical neural networks is that what's going to happen is we're going to have some light that's projected outwards. This sort of plane wave right here is going to represent some light. It's going to pass through a series of lenses, filters, modulators, and surfaces, and then it's going to just kind of travel through here, all these different plates, and it's going to arrive at some final output surface. And depending on where the light lands, we're going to say that it's going to have classified a task in a certain way. So for instance, if we're trying to figure out if a thing is a 1 or a 0, then we're going to take this plane wave, we're going to bounce it through a bunch of things. If it happens to land in this 1 slot, then we're going to say it's a 1. If it lands in the 0 slot, we're going to call it a 0. So what are the advantages of photons? Well, first off, we have low power consumption. Photons are not like electrons. They are massless. They consume much less power. And to actually drive these optical neural networks, you only need to drive this input plane wave and the output readouts. The middle layers actually can be entirely passive as long as you engineer them correctly. Now, in the same vein as low power consumption, you're going to have low heating. You're also going to have low crosstalk because photons at different wavelengths actually won't interfere when they're traveling, propagating across free space, unlike electrons and electrical signals, which will have lots of crosstalk and all that when they're sort of sitting too close together, and people go to lots of painstaking depths to sort of minimize crosstalk. In photons, we can sort of entirely kind of negate that effect. Photons are also fast. They travel at the speed of light. Yeah. Yeah, so this is actually, so there's multiple types of optical neural networks. There are on-chip optical neural networks where they kind of stick all these components on a tiny chip, and there are also these like really big, like diffusion-based optical or diffraction-based optical neural networks. So there's like really big plates that are like this big. I guess it sort of depends on the task. A lot of these, a lot of the research that's being done on these is kind of just like, we're gonna make the setup and then we're just gonna perform classification on like MNIST, which is the data set I showed above, which is a pretty simplistic data set, and people just like use it to benchmark. So I think when you go to like more complex tasks that require very complex encodings and all that, this might be very tough to actually set up. But in terms of just your more baseline simple tasks that a lot of people like to sort of look at, these are definitely going to be a lot quicker in terms of actually like performing the classification of like the photon traveling from here to like the actual classifications. Yeah, so how do we represent matrix multiplication with light? That's going to be sort of the primary thing we're going to talk about here. This has been a very big subject in this area in terms like we got to do matrix multiplication. We only have light that we can send out in various propagating intensities and stuff. So how are we going to do that? Let's say we want to do a multiplication of some vector B, which we're just going to say is 102, with some matrix A, which is a 3x3 of 101, 201, and 111. So how are we going to accomplish that? Well, we're going to take this vector B and we're going to load it into an LED light source array. And we're going to basically represent this 1, this 0, and a 2 by varying the intensity at which we send out these plane waves of light. So we're going to represent each value with a varied luminous intensity. Now imagine we have these three sort of plane waves traveling out into free space. Then we can shoot them into this. We can also make this spatial light modulator, which is sort of this point in the middle. And this spatial light modulator is actually a passive component. It's just going to have these various sort of materials that when a plane wave runs into it, sort of different physical properties of the plane wave are going to be altered. I can sort of give you a visual representation of that. So let's say I have a plane wave that's just traveling like so, and then it hits a chunk of spatial light modulator. What's going to happen is the spatial light modulator is going to cause some transform of the physical properties of the plane wave. So that can either be its amplitude or its phase. So once that goes in, perhaps when it comes out, it's going to be this. It's going to be at a higher intensity. So its amplitude will have increased, or it can be at a different phase. So perhaps it'll be like, okay, I can't draw a phase shift super well, but just imagine that the plane wave has phase shifted. So these spatial light modulators, if you give them sort of different materials and different densities, thicknesses, etc., at different chunks, you can actually manipulate how instant light is transformed as it comes out of it. And that can be done entirely passively. You don't have to sort of do any sort of manipulation on the fly or anything. You just machine this chunk of spatial light modulator, you stick it between your input incident light and your output, and you'll have a transformed sort of light plane wave. So now that we have these two pieces, we have to basically take our vector and prepare it such that it can actually be multiplied, aka pass through this spatial light modulator that encodes the matrix A right here. So what's going to happen is we're going to take our vector, this is the light coming out of the LED array. It's basically going to hit this lens. And what this lens is going to do, this collimating lens, is it's going to take this light that might be traveling in this weird way, and it's going to collimate it, aka it's going to kind of force it into this nice like vertical structure that we like here, where it's all in these neat rows that we can then tune accordingly to travel nicely into more components and then finally into the spatial light modulator. So our light's going to go from this light output array into this collimator where it gets sorted into these nice little streams. And then this collimated light that's coming out of this L right here is going to travel into a column lens. And what this column lens is going to do is it's going to cause the light, this collimated light that's kind of traveling like this, to disperse outwards so that it can then go into the correct dimension of our spatial light modulator out here. So you can see that our light source B starts out like this. It gets collimated into through lens L, and then this column lens then projects it into the proper dimensions to fit into the various rows of our spatial light modulator. And as our vector B, having been collimated and then messed around with a column lens, can flow into our spatial light modulator. The different areas of the spatial light modulator are going to interact with the various projected light waves of our initial vector, get transformed as sort of matrix operations would occur, and then they're going to get fanned back in with another column lens before they travel to the CCD camera, which will basically measure these intensities and get back a vector that represents the multiplication of our vector B with the matrix A. So this is sort of the baseline way in which people sort of achieved matrix multiplication operations with optical elements. And you can see here with each of these components, they just have to be set up first in this correct orientation with the correct materials, and then you don't actually have to drive any power through them anymore. They can be entirely passive. You just have to generate your LED light array, and you have to power your CCD camera so you can take images of the output vectors. And so you can see why this might be a lot more sort of power consumption, less sort of expensive when it comes to power consumption as compared to artificial neural networks. And there's actually nowadays a lot more clever ways in which this matrix multiplication occurs. I haven't really mentioned a lot of them here, but there are different algorithms that you can actually use to represent matrix multiplication. You can do it in terms of like convolutions, which enable you to use different optical components. You can also represent matrix multiplication in terms of Fourier transforms, which you can then use even more more simplified optical components to do. And that Fourier transform kind of thing actually also takes advantage of the fact that you can prove that optically you can do a Fourier transform with different lens elements and materials and whatnot at zero power cost. You don't have to consume any power to perform a Fourier transform with optical elements. But yeah, there's a lot of ways that people have explored when it comes to performing matrix multiplication with optical components. And so yeah, these sort of little sheets are an example of, I think these are diffraction optical neural networks, which rely on diffraction effects and these really big plates where light goes through and they hit at different points and then they go through all these different layers, which enable us to do these complex operations and get out basically a result that kind of mimics the classical artificial neural network matrix multiplication operation. So the two big components that comprise of a neural network are that matrix multiplication and then that activation function. So the matrix multiplication enables us to kind of transform our data in different forms, and then the activation function actually enables that big matrix to then get transformed into outputs that we want. So if we want to perform like a classification task, for example, of cats and dogs, as we talked about earlier, perhaps you'd have some big matrix of all these different values going in and out and all that. And then they would finally arrive at this activation function that would then transform the complex input into this more simple, maybe 2x1 matrix, where you have cats in the first element of the matrix and dogs in the second element, where the probability of a thing being a cat or a dog. So optically, we have to somehow figure out how to make these activation functions. The really, really key thing about activation functions is that they should have some nonlinearity in them a lot of times, because when it comes to neural networks, oftentimes you'll have lots of layers, and these layers may be linear, but if we stack just a bunch of linear layers and we don't introduce any nonlinearity, it's basically the same as doing a single linear operations. We could actually just stack all of them together. So we need some nonlinearity to actually be able to encode more complex tasks and to actually make it so that the sort of complexity of our neural network is actually being like represented. It's not just, we're not just doing redundant work for no reason. And nonlinearity in optics, at least at these power levels that we're using to drive these optical neural networks, is actually quite tough to sort of achieve. And so one of the principal bottlenecks of actually creating optical neural networks. So yeah, and the reasons being in that nonlinear components for these optics, they have to be able to handle the high power lasers that are driving operations. And also, current optical nonlinearity, it involves sort of a lot of non-ideal characteristics in that you won't sort of exactly get these pristine, perfect output forms. And that can mess with our sort of operations that we want to do when it comes to neural networks. Because for neural networks, what we really care about at the end is that the fact that we're getting these highly accurate outputs that are behaving mathematically as we want them to behave. So optical nonlinearity is a major bottleneck for achieving optical nonlinear activation functions. And we're going to discuss just a couple ways that folks have gone about trying to achieve this. So first, the low-hanging fruit is electro-optical neural networks. So we make all of the matrix multiplication components optical, and then for the activation function, we just stick an electrical layer in there. That's sort of your very lazy, like, I don't know what to do, I can't figure out optical nonlinearity. We'll just do it artificially, as we've always done with classical neural networks. Some actually, like the diffraction optical neural network, doesn't even use an activation function. It tries to sort of encode all the info in the actual plates. That's another sort of low-hanging fruit method people have tried to get around this with. And a couple examples of optical nonlinearity that are being used in optical neural network activation functions is, for instance, saturated absorption. So what is saturated absorption? Well, when light is incident on some absorptive medium, then absorption is going to occur. And as this light intensity increases, the absorption coefficient of the medium is going to decrease. And it's going to keep decreasing. And eventually, it's going to hit the saturation point, it's called, where the incident light goes to a high enough intensity on this medium where the medium will then saturate and then change behavior. It'll act differently from its unsaturated form. So you can actually induce nonlinearity that way by having some light come in, and it'll keep coming in until the intensity is so high that the medium saturates and then suddenly changes behavior. And you can see in these graphs, what's happening is you have some absorption coefficient here, alpha, and as intensity increases, it begins to decrease until we reach here, the saturation point, and then the medium changes its behavior and induces this different kind of point right here. And so you can see that we've generated this nonlinear shape. And if we mess around with it, we actually see that we can make it into something that looks like a sigmoid function, which is a very classical activation function that's used in neural networks. So that's one method of achieving optical nonlinearity. Any questions on that so far? Yeah. Mm-hmm. Okay, yeah, I should clarify that point actually. So the whole optical neural network thing, the training phase is actually all done on a classical, like artificial neural network. So we're going to figure out exactly what weights we need on the layers in order to perform the classification. And then we're just going to go machine our optical components so that the light will travel through these layers that have our prescribed sort of weights and biases. So we can't actually really train super well on these. Exactly. So let's say I want to make a cat and dog classifier. I'm going to go train my classifier on my laptop, and then I'm going to say, oh, these are the various layers and stuff I need. Then I'm going to go to the shop, machine them, and I'm going to stick them in my little chip or something. And then when I actually need to go figure out if something is a cat and dog, I'm going to shove that into my little optical chip. Yeah. And I think people are trying to figure out how to train on like actual optical neural networks, but that is really challenging because it's hard to be constantly reprogramming the like material itself. Do you have a question? Yeah, so actually, so the reason optical neural networks actually have seen a lot of attention lately is because we've really developed our technology in this area called quantum nanophotonics. So that implies basically we've gotten really good at machining these tiny components that go onto chips. So you can actually have a really nice optical neural network on like a really small chip. So I would say that they are actually viable if you want to like have these explicit machines that are going to only be running a certain classification task, and you're just going to make a lot of them. For instance, if I were like a company or something and I was doing these massive jobs that usually would take big clusters, take a lot of energy to actually perform, then maybe I can make a bunch of these optical chips. I would have to train them first on my computer, and then I can machine these chips and then just have them do the task, and they would be less consumption heavy. And I can get them fairly small because we're really good at the whole nanophotonics thing nowadays. Yeah. And then back to the nonlinear activation function part, we can use these things called phase change materials, which actually in concept are very similar to the saturated absorption idea. When this material undergoes this solid state phase transition. Maybe the instant light has some intensity that induces this phase transition. Then the optical properties of the material will then change a bit. So then maybe stuff coming through it later will act differently. So for example, this material, I think this is like, I don't even know what these elements stand for, GE2, SV2, TE5. It has an index of refraction of negative 4.7 prior to undergoing a phase change. But then when it actually undergoes a phase change, its index of refraction changes to negative 7.5. So you might imagine what that may look like for some sort of light traveling through it. The light's going to travel through it, it's going to be refracting a certain way, and then suddenly the light's going to maybe sort of affect it, excite it, or do something to it in a certain way that causes it to undergo a phase change, and suddenly it's going to refract the light in a different manner. And then from that sort of difference, we can then we can draw nonlinearity from it. And an example of this is maybe you can do something like a ReLU activation function, which is kind of this flat point, this flat slopeless line, until we suddenly hit this new point and a linear slope develops. If we were to kind of model that with phase change materials, you can imagine that when light is first coming in, and the material has not undergone a phase change yet, it's still flat sloped. And then when we induce the phase change in the material, then suddenly a linear slope occurs. So that's an example of how we can model a nonlinear activation function with a phase change material. So there's actually a few nice methods that we can use with these optical neural networks that actually enable us to do lots of kind of power-ups on our usual artificial neural networks. We can make them faster and more efficient. And the reason for that, and why people are actually so interested in optical neural networks, is that they can actually utilize a lot of the modern telecom technology that we have that A, enables really efficient manufacturing of these components, and B, enables us to use these techniques that are quite advanced and have been well developed in the telecom industry. So I'm going to give, I think it was two examples? Yeah, two examples of some technologies that can enable us to actually speed up the computations on optical neural networks as opposed to artificial neural networks. So the first example I'm going to give is this technique called wavelength division multiplexing. So this is a huge thing when it comes to optical signal processing. What's going to happen is, let's say we have these 4 different signals, and we want to perform the exact same operation on these signals. Maybe you want to multiply all these signals by 2. When we have these optical signals, we can apply this thing called wavelength division multiplexing, where we're going to take these 4 signals, we're going to multiplex them with this into one signal, this combined signal, and then we can actually apply our times 2 operation on the multiplex signal, demultiplex the signal, and end up with all 4 of them having the times 2 operation applied to them, but we've only multiplied one thing by 2 instead of having to do this times 2 operation all 4 of our signals. And this is pretty useful when it comes to neural networks, because as we talked about, neural networks involve a lot of repeated computation on various different matrices. So one technique that people develop is to basically just take these input matrices, multiplex them together, and then perform a single operation on them, and then demultiplex them to get their outputs. Originally, you might have had to perform 4 separate operations on 4 distinct matrices, but since we wanted to just do a single one, we can turn them into this giant, massive single signal with a multiplexer, do one operation, and separate them back out again. So in certain instances, we can do things a lot quicker with these methods. And these methods are fairly easy to implement just because they're so well used in a lot of different fields. Okay, we can do these parallel operations on multiple neurons with wavelength division multiplexing. Any questions on this so far? Okay, and then the second fun little thing here is this thing called a frequency comb. So a frequency comb is this pretty fun little instrument. Basically, it outputs from various bandwidths this spectrum of different light, and you can have different granularities frequency combs. But the nice thing about these is you can basically do as we were talking about earlier, where we want to generate these signals that we can represent as matrices. We can represent these really complex matrices with a single frequency comb. So we're just going to shoot out a bunch of different frequencies of light. There's going to be a lot of them, they're all going to come out at once, and we can manipulate all of these different frequencies to perform these matrix operations and whatnot with. So this is a pretty convenient way for us to generate those sort of initial vectors and arrays that we talked about earlier. Instead of having to, for instance, modulate an LED or an array of LEDs or an array of lasers or whatnot to kind of change them into values that we want to encode into vectors and multiply with, we can just use this big frequency cone, send out a wide array of signals, and then just manipulate those through some sort of filter that acts on different wavelengths of light to get them to the desired sort of output we want. So that's a really nice way to kind of do a lot of efficient operations that generate really big matrices when it comes to optics. And yeah, I think, so that's going to be the conclusion. We sort of today talked about two different classes of neural networks that kind of differ from our usual understanding of deep learning and machine learning, in that we see them as these kind of classical or electron-based things. Well, today we presented a quantum paradigm for machine learning, as well as an alternate mechanism for realizing deep learning that involves the use of optics. And both of these have sort of distinct advantages. In the QSVM case, we talked about how we can reach these high dimensional vector spaces with less bits and less sort of computationally expensive feature maps by using the quantum principle of superposition and using our qubits instead of classical bits. And in this ONN case, we've demonstrated how we can manufacture these sort of on-chip or on lab table neural networks that do not consume as much power and use less electricity, and can even provide some nice parallel computation and speed-ups along the way. So yeah, thanks for coming. We have a question in the chat. Oh, that's you. Wait, no, that's not you. It's a different hand though.